The next talk will be Uncertain Text Classification for Proliferation Detection by Drew Hollis.
Thank you very much. Yes, that's what I'll be talking about. It's going to be a little bit more on the uncertain text classification rather than the proliferation detection. There will be a great talk tomorrow by Carl Pasternak that will be talking a little bit more about the proliferation detection. So let's kind of just set the stage here.
You might have to. I have to get out of that. Okay.
Oh, there we go. All right. Yeah, let's set the stage here by talking a little bit about what text classification is. So we have some document XI that we want to classify to a set of classes. And the way we typically do this is we feed the document through a large deep learning model that is specifically designed for natural language processing tasks. We use one of the family of BERT models, which are really popular in the natural language processing world these days. And that spits out a set of real numbers, which are called logits, which are then passed through what's called a softmax function to map them onto the simplex to create actual class probabilities. And then we classify to whichever class had the maximum class probability. So we end up with something here on the bottom where we've got a document that we mapped to a set of class probabilities that we then assign to the highest class probability. So what we want to do with this project is we actually want to produce some kind of uncertainty quantification on those class probabilities. So something like a Bayesian posterior distribution on those class probabilities. So we can measure the confidence and uncertainty of our classification decision. And we want that uncertainty quantification to match three characteristics. First of all, we want it to be what's called well-calibrated. So with well-calibrated classification, we often take our maximum class probability as an indication of the confidence of our decision. So we might have a set of objects that were classified with a maximum class probability of 0.8, and we would want about 80% of those to be accurately classified. In other words, we want our confidence to match up with our accuracies. That would be what would happen with a well-calibrated model. With a poorly calibrated model, we might have objects that are classified with a confidence of 0.8, but their actual corresponding accuracy is quite a bit lower. So our confidence is not a good indication of what our confidence should actually be. We also want our model to have what we're calling good coverage. So as I said, we're going to construct something like a posterior distribution over the class probabilities that might look something like that figure on the left. And we can use that to construct a Bayesian predictive distribution over the class labels, which we can then use to construct a credible set over class labels, which is kind of like a discrete analog of the Bayesian credible interval. And as with credible intervals, we want that credible set to actually cover the true class label with some pre-specified probability that was used to construct the credible set. And so in a decision-making context, if we see these credible sets as kind of a set of plausible labels we would present to a decision maker, we want that plausible set to actually contain the true class label with some pre-specified probability. And then finally, with a lot of these classification applications, there's some kind of similarity structure among the labels, and we want our outputs from the model to actually reflect that similarity structure. So we want our class probabilities to reflect what we believe about class similarity. So if we had, for instance, a ranking of our classes by their similarity and then a ranking by their predicted class probability, we'd want those rankings to match up as much as possible. We could measure that with a metric called ranking accuracy. So that's kind of what we want to do. That's the goal of this uncertainty quantification. So how did we actually do that? We proposed a method called correlated belief matching, which is an extension of another method in the literature called belief matching. These are both instances of something called variational inference, which is another way of doing Bayesian inference where we assume the prior for our quantity of interest, but we also assume the form of the posterior distribution, and we essentially fit the parameters of that posterior distribution using what's called an elbow loss function, which is what that formula is down there at the bottom. So there's a lot of math here, but the main points I want to point out is, first of all, our quantity of interest is the logits, the z's, which are the real numbers that as I mentioned, immediately precede our class probabilities. And there are kind of some key quantities that I want to point out here. First, in our prior, we have a sigma naught, which is the variance of the prior that's essentially controlling the strength of the prior and its regularization effect on our output. This allows us to essentially control the calibration of our model. We also have this prior correlation matrix, which allows us to encode information about class similarity. The logits actually correspond one-to-one with the classes, so we can use that to encode that similarity information and enforce that interpretability requirement that we want. And then with the actual evidence lower bound loss function, there's a term here at the end, the H term, which is essentially the entropy of the posterior distribution. Entropy measures the uncertainty or the variability of our posterior distribution. By adjusting that phi coefficient, we can lead to or get a more or less variable posterior distribution, which allows us to control that coverage element. So those are the main players here that allow us to accomplish what we want to accomplish for uncertainty quantification. So to look at some results, we have here this figure on the right is a plot of the coverage values versus the calibration error values for our proposed correlated belief matching framework and the original belief matching framework that we're extending. And you can see that for our approach, we're able to achieve a high coverage while also maintaining a low calibration error compared to the original belief matching framework, which has to kind of settle for a high calibration error in order to achieve good coverage. And so we're able to obtain a much better trade-off between these two metrics using our approach. Looking over at the table on the left too, looking at the ranking accuracy row, you can see that our approach also allowed us to obtain more interpretable results as measured by ranking accuracy. But I think one of the other really key takeaways and advantages of this approach was the computational time. So dropout is another method that we compared our approach to in addition to the original belief matching framework. Dropout's kind of a standard approach that's used a lot in deep learning for uncertainty quantification. And when we looked at the computational cost of actually constructing the posterior distribution, it took about less than half a minute for us to construct 200 posterior samples using our approach. And it took almost an hour to produce the same posterior distribution using dropout. So that's a significant computational advantage. So to summarize, correlated belief matching allows us to obtain uncertainty quantification that's well calibrated, has good coverage, is more interpretable than a lot of the other existing methods, and has a lot of computational advantages over other typically used uncertainty quantification approaches. With that, I'd like to thank our funding sources, and that is all I have. Thanks.
No time for questions or not?
One quick one while we're switching. Go ahead and come up and
So I noticed that you broke things down into like 4 or 5 different categories. Nuclear physics, something we want to know.
Yeah.
What if I put in a text that had nothing to do with any of those categories?
So I would assume that it would also depend on kind of what your training data looks like. So it would depend on whether those categories were also part of your training data. If your training data didn't contain an additional kind of unrelated category, the hope would be, and we didn't actually test this, but the hope would be that that would receive a lot of uncertainty, just because it's kind of a sort of the black sheep. It doesn't really fit with a lot of the other data that comes for training. So we would expect there to just be a lot of uncertainty as to what a text from that category would be.
I guess like on your current training, let's just talk about the current training that you have.
I'm going to say I need to cut it off, but I'm hoping that we'll have some time at the end of this.